You know that moment when you're in the middle of a game and you just have to stop and look around? The world is just stunning. The light, the details, everything. It feels so incredibly real, like you could almost reach out and touch it.
But that brings up a really cool question. How does that happen? Because this scene right here, this amazing looking world, at the end of the day, it's all just data, billions and billions of ones and zeros on a chip. So how in the world does a computer perform the magic trick of turning that code into a world that feels alive?
Well, for starters, what you're seeing isn't just one flat picture. Oh no, it's an incredibly complex construction. This single scene is built out of more than 2.1 million individual points floating in 3D space. These points are called vertices.
And what do you do with a bunch of dots? You connect them. All those points are linked together to form a mind-boggling 3.5 million triangles. That's right, triangles. They create the basic wireframe skeleton for every single object you see on screen.
The whole process that turns that massive triangle skeleton into the final, beautiful image is basically a super fast, highly optimized assembly line. And in the world of computer graphics, this assembly line has a name: the rendering pipeline.
So that's what we're going to do. We're going to follow the amazing journey of just one single frame as it zips through this pipeline, starting as a bunch of 3D data and ending up as that gorgeous image on your screen.
And really, this whole incredible process boils down to three main stages. This is the secret sauce behind almost every game you've ever played. First up, we have to place all the pieces. Then, we paint in the pixels. And finally, we add all the realistic light and shadow that makes it pop.
Okay, let's dive into step one, placing the pieces, or what's officially called vertex shading. The big goal here is pretty straightforward. Figure out where every single one of those millions of vertices is supposed to show up on your flat 2D screen.
So the game's engine is taking the 3D map of the world and just crunching a ton of math to project it all onto your 2D monitor. Now, here's a funny thing. Even though it's called shading, this first step has nothing to do with light or color just yet. It's all about position. Think of it like you're taking a photograph of a huge 3D model. This step is just about figuring out what the camera sees and where it sees it.
And you know, every single vertex goes on this little mathematical journey. It starts in what's called model space, which is just its own little coordinate system. Then it gets placed into the game's world space. After that, the computer figures out how it looks from the camera space. And finally, bam, it lands in its final position on your screen. And remember, this whole trip happens for millions of points, all in a fraction of a second.
Okay, great. We now know where all our triangles go. But right now, they're just empty outlines. We need to fill them in. And that brings us to our next step: painting the pixels, also known as rasterization.
Rasterization is where those triangle outlines get turned into actual colored pixels. Your GPU looks at every single triangle and basically asks, all right, which of the millions of pixels on this screen are inside your borders? Then, for every pixel that's inside, it paints it the right color. It's like a cosmic, lightning-fast game of paint by numbers.
But wait a minute. This creates a new problem. In our scene, the train is obviously in front of the station. So how does the computer know not to just draw the station's triangles right on top of the train's triangles? How does it figure out what's in front and what's behind?
The solution to this is so clever. It's called a Z-buffer. Just imagine that for every pixel on your screen, the computer keeps a little note of how far away the object is from the camera. It's like a depth map. So when a new triangle comes along, the GPU just checks that note. It asks, hey, are you closer to the camera than what's already here? If the answer is yes, it gets painted, and the note is updated. If it's farther away, it just gets thrown out. Simple as that.
And that's really the whole secret right there. This simple depth check is what makes sure the world looks right. It's a bit of a brute force approach, but man, is it effective. It guarantees that things in front correctly hide the things that are behind them, just like in the real world.
So at this point, we have a perfectly layered image, but it's still looking pretty flat and lifeless. This final step, fragment shading, is where the real magic happens. This is the step that breathes life into the scene and makes it look realistic.
I mean, just look at the difference. It is absolutely dramatic. Before, we have a flat, colored-in shape. After, whoa! Now it has depth, highlights, and shadows. The GPU is calculating how light from the game's sun would bounce off every surface. This is what makes metal look shiny and what makes things look solid and real. It's what tricks our brains into seeing a 3D object.
To pull this off, the computer needs one critical piece of info for every single triangle. Which direction is it facing? This is called its surface normal. And the easiest way to think about it is to imagine a tiny little flagpole sticking straight out from the face of the triangle. That flagpole is the normal.
And the logic from here is actually pretty intuitive. The GPU just calculates the angle between a light source, like the sun, and that tiny flagpole. If the flagpole is pointing right at the light, the surface is going to be bright. If it's angled away from the light, it's going to be darker. It's that simple.
But this creates one last little puzzle. If every flat triangle gets one solid shade of light, then curved objects would look really blocky, kind of like a disco ball. So to fix this, developers use a really neat trick. Instead of having just one flagpole for the whole triangle, they calculate one for each corner, each vertex. That corner's direction is an average of all the triangles connected to it. This lets the GPU create a beautiful, smooth gradient of light across the entire surface, giving us those realistic-looking curves. So we've walked through the whole process step by step, but the part that is truly mind-boggling is the sheer blistering speed at which a modern graphics engine does all of this. That entire three-step pipeline we just discussed, placing millions of vertices, filling in millions of triangles, and calculating light for millions of pixels, that doesn't just happen once. In a high-end game, that whole process can happen 120 times, every single second. To put that into perspective, your computer has to build every single frame you see from absolute scratch in a little over 8 milliseconds. The amount of computational horsepower you need to do that is just immense, and it's exactly why modern GPUs are some of the most complex processors humans have ever built. And of course, the technology never stands still. We're now getting into even more advanced stuff, like ray tracing, which simulates the actual physics of light for hyper-realistic reflections and shadows. We've got AI-powered tech like DLSS that can magically boost performance. Modern GPUs actually have specialized hardware inside them dedicated just to doing these specific jobs.
So it kind of just leaves you wondering, right? We've gone from simple blocks to near photorealism in just a few decades. As this rendering pipeline just gets faster and smarter and more powerful, what's the next frontier? What will the virtual worlds of tomorrow even look like? It's pretty incredible to think about.